So the standard enthalpy change for a reaction, we looked at that in Chem 1A. This is a change in enthalpy for a process in which all the reactants and products are in their standard states. So review of standard states. Standard state for a gas is the pure gas at 1 atmosphere of pressure. A liquid or a solid would be the pure substance in its most stable form at 1 atmosphere and the temperature of interest, which is generally 25 degrees Celsius room temperature. For a substance in solution, the standard state is a concentration of 1 mole per liter. Can all substances that are in solution have a concentration of 1 mole per liter? Is that even possible for all substances? No. Some things don't have a molar solubility that's that high. But this is still the standard state, because it's not actually a real thing. It's in our imaginations. So we can talk about standard entropy change. Change in entropy when everything is in their standard states. Because entropy is a state function. So the entropy for the reaction is going to be the entropy of the products minus the entropy of the reactants. Again, delta is always final minus initial. The products minus the reactants. So we've got this now, but we need to define what these things are. What is the standard entropy of the products? Not the change, which is the standard entropy. So these are called standard molar entropies. So, like other things, we define where 0 is because we can't calculate absolute values for enthalpy, and there's actually no absolute 0. But what we're looking at is changes in entropy, and so we don't exactly where 0 is doesn't matter as long as we all agree to use the same place. So third law of thermodynamics, the entropy of a perfect crystal at absolute 0 Kelvin, is 0. So perfect crystal, there's only one way to arrange the components, right? And Boltzmann's definition of entropy was S equals K times the natural log of W. So here we end up with W is 1, and so the entropy is 0. So that's our definition of 0 for enthalpy. Okay. I said earlier, for entropy, there is no absolute 0. And right there it says, for entropy, there is an absolute 0. I can't even read today. My bad. There is an absolute 0. Gosh. I am serious. If you see me do stuff like that, just call me on it right away. And if I'm right and you're wrong, I will not make fun of you. Have I ever made fun of you guys? Not really, no. Maybe a teeny bit, but yeah. Okay. So entropy is a state property, state function. It is also an extensive property. It depends on how much substance there is. Yeah. So we've got a table here, standard molar entropy values for selected substances. So hydrogen gas, argon gas, all these different things. Here we've got gases. The units are joules per mole Kelvin. Here we've got some liquids and some solids. So we can look those things up. So 25 degrees Celsius, the standard entropy of any substance, is the energy dispersed into 1 mole of that substance. So that depends on the number of places to put the energy. So that's going to be affected by the state of the substance, its molar mass, which allotrope it is, and the molecular complexity, and the extent of dissolution. Do you remember what an allotrope is? different forms of the same element. So for carbon, we've got graphite, and we've got diamonds, and then there's buckyballs and graphene and all those other really weird things. Those are considered allotropes. They are all pure carbon, but the carbon atoms are arranged differently. Sulfur, you can have element just S, or you can have S8. Those are examples. Okay. So the entropy of a gas is usually larger than the entropy of a liquid. That makes sense, right? Entropy, just in a very broad sense, is disorder. In a gas, the particles are more disordered, more spread out than they are in a liquid. And a liquid will have greater entropy than a solid. So gases have more energetically equivalent ways to arrange their components. They have more modes of movement available to them. So we see the comparison for water here, that for water in the gas state at the same temperature, the entropy is significantly larger than in the liquid state. We see a relationship between standard entropy and molar mass. The entropy for the noble gases increases with increasing molar mass. Why is this? The energy states that are associated with the motion of heavy atoms are more closely spaced. And so that allows for more dispersal of energy because the different places to put them are closer in energy. A trend like this only holds if all of those substances are in the same state. If you were to look, come on, there we go. If you were to try to compare liquid xenon with gaseous krypton, you can't do that. So allotropes, some elements exist in more than one form. And the entropies of these things are different because the arrangements of the atoms is different. Diamonds are a covalent network solid in which the carbon atoms are all covalently bonded to each other in a three-dimensional lattice. Graphite is also a network covalent solid. The atoms are bonded to each other by covalent bonds, but now there are thin sheets, and those thin sheets are held together by intermolecular forces. And so the graphite has more variability. It's less constrained in its movement than a diamond is, and so its entropy is greater. Does that make sense? You kind of think of it as wiggle room. How much can the atom wiggle around? Well, here the sheets can actually slide past each other, and so that's a lot more wiggle room than here, where everything's kind of stuck.
So the more you can wiggle, the greater your entropy?
The more you can wiggle, the greater your entropy. Mm-hmm. Because entropy is different places that the energy could be put that are at the same level. You can also think of it as different ways of moving. So you can have an atom that vibrates. You can have an atom that travels through space. You have an atom that spins. If you're talking about a molecule, the bond can stretch and constrict. And so those are different places that the energy can be put. So here, carbon atoms cannot move relative to each other, but in the graphite they can, because these layers slide. That's what makes graphite slippery, makes it useful as a pencil lead, because as you drag it across your paper, it leaves part of it behind. Diamonds don't work so well that way. They tend to just cut through the paper. Yeah. Any other questions? Yeah, I keep getting ahead of myself. So for a given state of matter, entropy will generally increase with increasing molecular complexity. And that's because you get more places to put the energy. So we've got translational motion, movement through space, and that could happen in multiple directions, right? We've got rotational motion that's spinning around, and then vibrational motion, where here with this molecule, the two atoms in the molecule can stretch and constrict, and that's called vibrational motion. Looking at these two substances, argon in the gas state and NO in the gas state, their molar masses are comparable, but NO has a much or significantly higher entropy. They both have translational motion, rotational motion, but argon also has vibrational motion. Thank you. See, I was testing you. Argon does not have vibrational motion. Nitrogen monoxide does. The molecule can do this, the atom cannot. Okay? So that's why the molecule has more entropy. So the more complicated the molecule, the more types of vibrational motion you have within it, and so the greater the entropy. So comparing carbon monoxide and ethene, C2H4, their molar masses are almost identical. They're both in the gas state, but C2H4 has higher entropy. Why is that? It's more complex. So carbon monoxide is just carbon and an oxygen. Ethene has a structure like that. So for carbon, you can have vibrational motion with this bond, but in this molecule, you can have vibrational motion in all of the bonds. And so there's more complexity, there's more different places to put energy, and so the entropy is larger. Yeah?
Does the molar mass have anything to do with the...
Yes, the molar mass can have an effect. We looked at that here where we were just comparing noble gases, and we see that as the size increases, so does the entropy. Good question. Down below we have three compounds of the same two elements, nitrogen and oxygen, and we've got nitrogen monoxide, nitrogen dioxide, and dinitrogen tetroxide, and we see that the entropy is increasing. Here we've got molar mass increasing and molecular complexity increasing, so of course the molar entropy will also increase. The extent of dissolution affects the entropy. So when you dissolve a crystalline solid into a solution, say into water, that will generally increase the entropy, which should make sense because now we took this solid crystal where the ions could not move relative to each other. There was really no translational motion at all, and not any rotational motion either. And now we're separating them from each other. Now they can move relative to each other, and the larger things like that chlorate ion can rotate as well, and so we have more places to put the energy. The energy also becomes more dispersed through the entire solution, so it's more spread out. Increasing in entropy is increasing in energy dispersal and spreading out. So we see that the solid substance versus the same substance dissolved in water, the entropy increases with the dissolved. Any questions? So calculating standard entropy change for a reaction takes on the same form as calculating standard enthalpy of reaction. So many E's. So it's a state function, and so we can take the entropy of the products and subtract the entropy of the reactants. It is also an extensive property, and so it depends on the amount of substance, so we need to multiply by the coefficients in the balanced chemical equation. This molar entropy is per mole, and then we're multiplying by how many moles are involved in that reaction. A big difference here from calculating standard enthalpies is that at 25 degrees Celsius, standard entropies are always non-zero, whereas standard enthalpies often were zero for elements, right? And so you could just leave all the elements out. Here you can't leave anything out. Let's practice. Calculate the standard entropy change for this balanced equation. So we're looking at the entropy of the products and subtracting the entropy of the reactants. That gives us the change in entropy. So the standard entropy change for the reaction. I'm going to take the products. So I have 2 moles of water. So I'm going to multiply 2 moles of water by its entropy, molar entropy, 188.8 joules per mole Kelvin. And the moles cancel out. And then I also have 2 moles of sulfur dioxide. So I'm going to multiply by the standard entropy, standard molar entropy for that, 248.2 joules per mole Kelvin. Again, the moles cancel out. Products minus reactants. So then I'm subtracting the reactants. So 2 times 2 moles times the molar entropy for H2S, 205.8 joules per mole Kelvin, plus 3 moles times the molar mass, standard molar entropy for oxygen, 205.2 joules per mole Kelvin. Okay, I'm coming up with minus 153.2. Anybody else? Quiet murmurs of assent. And that'll be joules per Kelvin. These standard molar entropies are always positive because 0 is pure crystalline structure at absolute 0, right? So these are always going to be positive, and whether the change in entropy is positive or negative depends on the relative entropies of the reactants and products. Are we changing them to things with higher entropy or lower entropy? Any questions? Would this negative number definitely tell us whether this reaction was spontaneous? No. We need to look at delta G. So that's going to combine delta H and delta S. So it really depends.